All right, welcome. In this video, I want to continue sort of where we left off in the last video. It's a good idea to maybe take a look at the last video if you haven't already. In that one, we posed a problem about scheduling classes to classrooms using the common sense constraint that no two classes can be in the same classroom at the same time. So we already took a look at one algorithm to solve that, and we called that Alice's first fit algorithm. We determined that it was correct and that it took n log n operations in the worst case if we're clever, n squared if we just follow a straightforward implementation. And I want to continue that discussion in this video where we're going to now look at a second algorithm for it, which I'm calling Bob's best fit algorithm. And it involves a subproblem, and really the focus of today's subproblem will be, or today's video will be on that subproblem, which is what I call the non-overlapping intervals problem. It's also known as sort of the maximum non-overlapping set, or there's a couple different names for it. So if you take a look online, you might encounter it under a different name. Let's take a look at where we sort of left off in the last video. So we want to look at Bob's best fit algorithm for scheduling classes, and as I mentioned, the scheduling classes problem is trying to schedule non-overlapping classes to classrooms so that we can minimize the number of classrooms that we use. So Bob's algorithm, or Bob's presented algorithm, is one where So Bob's best fit algorithm, the one that we have outlined here, proposes that what we do is we select the largest collection of compatible classes, and then we place them all into a single room. And the idea is that if we take that largest collection of classes, that will lead to the minimum number of rooms needed. And this is just following sort of a principle that we sometimes apply. If we're sort of taking bytes out of something and we want the minimum number of bytes, we want to take the largest bytes. If we take the largest bytes, that will lead to the minimum number of bytes. And that applies in a lot of sort of optimization problems where we want to apply a greedy algorithm. The most common and obvious one of this is the coin changing algorithm that you use to make change if you've ever worked in retail, by selecting the largest bill or coin that you can use to make change, subtracting that value and repeating. So that's just the principle applied here. Let's look at a quick set of pseudocode that I've whipped up here. Now the pseudocode is actually not adding too much to this, other than what I want to do is focus on sort of this one step where we're finding the largest collection of compatible classes. And it's just because we want to highlight this. This is the problem we still have left open and we don't really know how to solve. Otherwise, we're going to start with an empty set of classrooms and we're just going to iterate, find that largest collection of compatible classes, and assign them all to a new classroom. So every loop here, we're going to have one more classroom. And so we're going to see we're going to have about D loops if there's D classrooms. But we haven't really said what we're doing here, what this sort of inner step is. And this inner step is likely going to use a loop 2. And it's probably going to be about looping over all of the classes. If we're trying to find the collection of classes, at least we're going to probably have to look at all the classes. So there is some hidden inner loop here, but we can probably anticipate that if our upper limit on D is n as well, we got maybe n and n, okay? And I haven't included in the pseudocode a possibility that we might want to pre-sort our set of classes, which means even if this is sort of n and n squared, we might be spending n squared operations or n log n operations just to sort our set of classes to start out with. Okay, so that actually proposes for us a new problem. And I'm going to state this as an input-output criteria so that we can sort of approach it as a problem, a separate problem in itself, which is to find this maximum set, this largest collection of compatible classes, or as I'm going to state it here, the maximum non-overlapping set of intervals. So this problem, as I've got stated here, is going to have the same input that we had for the scheduling problem. Just a set of classes, start and finish times for n classes. And then the output is different. Of course, it's a different problem. In the scheduling problem, we're trying to minimize classrooms. Well, now we're going to try and maximize classes. So we're going to find the maximum number of classes, and then I'm going to pick out those classes by just selecting a subset of C. So give me that subset. And if that's the maximum number of classes, then I want the subset to be that size, the size M. And then I have to bring in the criteria of non-overlapping. What does that mean? So I could have just written, non-overlapping, but I want to sort of formalize what that means. So if I pick two classes, if I pick Ci and Cj, and they're both in the set that I've selected out, A, not necessarily in C, but the ones that I select should not overlap. So I pick those two out. If that's the case, then either class I finishes before class J starts, so Fi comes before Sj, or the other way around, class J finishes before class I starts. One or the other. If both of these are not true, then that means we have an overlap in our class. So we're going to use this additional criteria to say that those two classes don't overlap. And notice I've just picked any two classes out and said they don't overlap. That means they're mutually compatible. And that's what we should expect. That there shouldn't just be some other class in the set that I don't overlap with, but I can't overlap with any other. So pick any two, then this should be the case. Okay. Again, maybe we might just highlight that this gives us some criteria of validity or optimality for our problem. So validity is a subset and non-overlapping. The optimality is that the size of our subset must be equal to our maximum number of classes. Okay, so Bob, we're going to say, has come to us for our help. His algorithm that he came up with, he thinks is going to work, but he doesn't know how to solve this problem, the non-overlapping sets problem. And in fact, he says, I've come up with a couple of different algorithms, and I don't know which one we should use. So he's got a few. He says I could select the class with the earliest start time. So that's sort of similar to Alice's algorithm. Maybe he's copying Alice here. It says I'll just pick the earliest start time and keep adding them to my maximal size set as I go. Eliminating any that I overlap with. Or I could do that with the latest start time. He says, I don't really know which one is going to work here. Earliest start time, latest start time. And if you're sort of following along and you're thinking a little bit cleverly here, you might say, hey, if we just sort of reverse all start and finish times, sort of reverse time, start at the finish times and go backwards, then we have two other algorithms here. We could have earliest or latest finish time as well. And they're sort of partnered up. Okay, if one is right, then if the earliest start time algorithm is correct, then the latest finish time algorithm should be correct, because it's just the same algorithm run backwards. And same thing here. If the latest start time algorithm is correct, then the earliest finish time algorithm should be correct, and that's just running this one backwards again. Okay, so that's changing earliest to latest and start to finish. Okay, you got to swap both of them to get the parallel algorithm. These two are not parallel algorithms. One could be correct and the other one could be wrong. Okay. Bob says, what else could we do? We could also just say, hey, short classes are probably not going to overlap very much, so why don't we just pick short classes where you might be able to get a whole bunch of them in the classroom. So that could be a possibility. Or he says, well, maybe another way of getting the maximum size set of classes is just pick the class that has the fewest number of overlaps already. So by picking it, we know we have the maximal number of other classes to pick from, and that might help us maximize the size of set we can get. So Bob basically says, well, I don't know which one of these is correct, Are any of them correct? We don't know. And so, of course, faced with this problem as a greedy algorithm sort of a designer, we have to search for our proofs of correctness, or if you like, our counterexample, which is, again, as we go on, we might want to split our focus into both directions. Or say you're on a team, then maybe one of you should be focusing on one direction and another focusing on the other direction. But make sure you stay in communication, because as I mentioned in the last video, if you're having trouble down one of these paths, it might give you insight as to how to succeed on the other path. And so that's why I suggest going down both paths at the same time. Well, let's do this here. And in fact, I've sort of designed things to be not too hard to figure out here, because I've designed this input. As I mentioned in the last video, I put some effort into designing this. One, to look like the Starship Enterprise, because that's fun, but also to make sure that this input serves as a counterexample for any of the algorithms on this list that happen to be incorrect. And of course, I knew ahead of time which ones were incorrect, so I designed this input to do that. So what that means is, for our purposes, all we actually have to do is run these algorithms on this input. And if we do, then if some of them will probably give us worse solutions than others, and the ones that give us worse solutions are obviously not optimal, so we will rule them out. So let's start with this one, earliest start time. So if we're going to select the earliest start time, so that's obviously this class here, so I'll select that one. And then after selecting it, the next thing we do is we obviously can't select any class that overlaps with it. So any class that overlaps with it, I'm going to rule out. Right. Then we select the next one with earliest start time. And again, any class that overlaps, we rule out. We'll do it again. And that looks like we're out. So it looks like we've ended up with 3 classes here. Now, some of you might already notice that we can do 1, 2, 3, 4 right here in this set here. So this algorithm incorrect. Earliest start time does not work. It worked for Alice's algorithm when we were facing a different problem. That was the order we considered our classes, but this one, no, it doesn't work. Okay, let's try the next one. Always select the class with the latest start time. Okay, latest start time looks like this one here. Okay, let's do it. So our latest start time. Again, rule out any that overlap, but we'll do latest start time again, which looks like this one. Again, I'm just going right to left now, okay, picking start time. So that one there, and rule out any we overlap with. Okay, right to left, earliest start time. Okay, looks like we get this one again, right to left. Rule out the overlap. This looks like a tie, but looks like I'll pick that one. Rule out overlaps. Okay, we still have some non-overlap. Now these all overlap with each other, so we can only pick one. But we're going to pick the earliest start time, which looks like, or sorry, latest start time. This one here, and rule out our overlaps. Okay, now this gave us 1, 2, 3, 4, 5. That was better than the 4 we just kind of used in our last counterexample. And hopefully, maybe the way we've colored them in here makes it easier to see that this really is the optimal. There's no way we could get 6. Okay, so this is actually the correct algorithm if you're keeping track. Okay, latest start time. Earliest finish time is also a correct algorithm, and if you want, you could try and run that on this as well. You'll get a different set, okay, a different set, but let's see why. So earliest finish time I think would start out by giving us this one here. It would rule out the other ones, and then it would pick one of these 3, and I think it would be, those 3 would be tied. So there's a tie there, but let's say it picks this one. The only difference we're going to get, I think, yeah, we'll pick this one next and then these 2, is we'll swap out this one for one of the ones we could have swapped it out for. So actually running the reversed correct algorithm would give us a slightly different output in terms of different classes, but the size would be the same. It's also optimal. Okay, let's continue and see if any of these other algorithms work. Okay, next one, we're going to do the shortest duration. Shortest duration, I've kind of designed this on purpose. It's hard to see just visually without numerical representation, but I've intended this one to be the shortest duration. So by selecting it, we rule out taking these two. Again, I designed this on purpose because we needed those two if we were going to get our maximum size set. So we'll actually see here, I guess I'm going to select that one as my next shortest. Again, there's sort of 4 all ties here, so I'm not sure. But that rules out these ones. Now it looks like I can pick one of these two, and that allows me to pick the other one. But I've only got 4 instead of 5. So again, no, failure on this one. This is not a correct algorithm. Okay, so we'll proceed now to our last algorithm. Fewest number of conflicts. Again, it might be a little bit hard to see. We'd have to go to each one and count, but by design I've made it this little one here. It's only got 1, 2, 3, 4 conflicts, and we can see some of these other ones are going to have, are at least going to have 4 conflicts as well. So I'm hoping that this is the one that we're going to pick out. And again, by selecting it, we rule out the ones that we want to select. And again, least number of conflicts, I think it's going to be one of the ones over here because these ones all conflict with each other. So it looks like maybe it's this one. So we'll pick up that one. Take out all the ones it conflicts with. Now least one is one of these two. We only get one but not the other. And then any one of these ones. So I guess I picked this one. Again, our output here is 4. And so by picking this case, we actually end up with, yeah, incorrect. Okay, so that's sort of non-standard. Normally when we're going to face, an algorithm, we're going to want to come up with a counterexample instead of relying on some big input to just work for us. Usually if you just randomly pick a big input, all kinds of algorithms might work for it. So you don't know. That's not going to help you rule out. So instead, I've decided here to provide ourselves with some counterexamples. And the first one is going to be for algorithm 1. Now that one says always select the earliest start time. So my idea behind this one is just because it starts early doesn't mean it doesn't end late. So we could pick a really long class that sort of takes up the whole day, and then of course we could fit other classes in there. We could probably do that with a few number of classes. I've decided 3. So one long class that starts early and ends late, and 2 shorter classes that could fit in there. So algorithm 1, counterexample, pretty easy to find. Algorithm 2 is correct, so we can't find one, so don't waste too much time on that. What about the shortest duration? Okay. Well, actually, this counterexample works the same if I can just shrink this one down. I'm going to shrink it down and put it here and here, like this. Okay, maybe a little longer. But the shortest duration, as long as it prevents me from taking 2 longer ones, then that's not the case either. Now, my counterexample for the least number of conflicts, this is a good example that when you're working with these greedy algorithms, you might have a problem. You propose a greedy algorithm and you find a counterexample. You say, okay, that didn't work. And then you think, oh, there's a different greedy algorithm. I'll try that. It doesn't work. And as you start ruling out your greedy algorithms, you start getting more clever with them. Well, okay, I'll pick the first one that is, greater than the second one but larger than the third one, something like this. Adding more and more constraints to it. Well, as you do, you make your algorithm more tricky and clever. Well, you have to be more clever with a counterexample then, and your proof. If it turns out being correct, you have to be more clever with your proof. Well, in this case, selecting the one with the least conflicts is kind of a more clever algorithm. And to find a counterexample like we did with just the big one is a little bit harder. We have to design it to pick ones that we don't want first. So I've actually come up with this counterexample. And the reason, and I've drawn it in this way on purpose so that we can see that the maximal size set should be pretty obvious as 4. Okay. But we will not be able to select that set if we select this one here. Okay. And this one only has 2 conflicts, right? But it conflicts with the 2 that are critical for our largest set. Okay. So because we would select it instead of the 2 it conflicts with, they don't conflict with each other, right? it prohibits us. So we'll pick this one first. Once we do, we eliminate these two. Then it's sort of a free game what we pick from each side, but we can only get 3 instead of 4. I don't know if this is the minimal size one counterexample. It's the minimal size counterexample that I could come up with, but I didn't try very hard to come up with it. I sort of stopped when I found it. So there might be a smaller one. If you can come up with a smaller one, let me know. Okay, but let's continue. If we've ruled out algorithm 1, 3, and 4, then what we probably want to do is focus in on algorithm 2. All right, so our goal here is to prove correct algorithm 2, I guess, for our non-overlapping set problem. So again, I've crafted a theorem here by trying to describe the algorithm. I've just said always selecting the non-overlapping class with the latest start time, that was the algorithm that we defined, okay, will result in the maximum set of non-overlapping classes. So remember, we sort of have 2 clauses here. The first clause is saying what your algorithm does, always selecting the non-overlapping class with the latest start time. The second clause, usually borrowed from the problem statement, tells us what it is to be correct for that problem. In our case, maximum, that's part of it. Remember, that's the optimality part. Non-overlapping classes, that's the validity part. Again, we've just sort of borrowed that from our problem statement. So again, on a very general abstract level, we're saying our algorithm is correct for our problem, but we've gone and we've looked at our algorithm to see what it does, and we've looked at our problem to see what it means to be correct, and we've used that to craft the statement for our theorem. Okay. Again, as I mentioned, I think in a previous example, that if our algorithm is more complex than a single clause, same thing with our problem, then we might just define them above algorithm 1, problem 1, and say algorithm 1 is correct for problem 1 with references to the more complicated definitions above. But for the problems we've been encountering, at least a lot of them, since we can describe the algorithm and the problem's correctness in a single clause, one sentence will do. Okay, so let's continue. And then remember, our first step is to try and protect the generality of our proof. So we're going to start with an arbitrary input. So in this case, we're just going to assume our input is an arbitrary set of n classes. Don't say what n is. And we'll proceed with no knowledge other than what we assume is true of the input. Okay, again, we want to begin these proofs by giving ourselves something to talk about. So I'm going to let P, once again, we're using S's for our start time, so I don't want to have any confusion with them. So I'm going to use P instead of S. Usually I'll use S for solution, but I'm going to use P here. So I'm going to use P, and unlike in our last video where these were capital P's standing in for sets of classes, these are now actually classes. Okay, so P is just going to be this subset of all of the classes that we select as our non-overlapping set of classes. Now we're going to select, we're going to let P be the one selected by our algorithm, okay, and we're going to keep them in descending order of start time. That's the order that we would have added them into this solution. So even though I have it set here as a set, for the purposes of analyzing the set in this proof, we're going to keep them in descending order of start time. Okay, now again, like we've seen in our last couple proofs, we're going to want to compare this solution to an optimal solution. So I'm going to set up O here, my optimal solution. My optimal solution, as before, because the size of our solution is going to determine whether we're optimal or not, I'm going to assume here that we have different size solutions, and that's because we don't want to beg the question by assuming that we already have an optimal size. Now, I've used D for the size of our solution. That's the one we're sort of unsure of. M is the maximum size, so we'll use that standing in for the size of our optimal solution. So it's a maximum size set of non-overlapping classes. And again, for the sake of comparison, I'm going to keep this set also in descending order of start time, so that they're both in the same order. So even if we're not selecting the same classes, we know that both of these ones are the ones that start the latest, and then these ones are the ones that start the earliest. Okay, so we'll continue. Now, again, a lot of this is set up, and I mentioned that a lot of proofs you might encounter online will maybe just throw this part away, assuming you could fill in these gaps yourself. And if you do have some discrete math background, you might fill in these gaps no problem. But the next step of the setup is to say, give us something to talk about. And so we're going to assume that this first location that they disagree is going to be when they pick a different class. Okay, so our solution is going to pick the class PI, but the optimal solution is going to pick the class OI. And now we're just going to consider possibilities of what relationships we might have. Now, in general, I'm going to only pick two cases here, but in general, when we have two things that we're comparing in this way that are numerical in their values, we can have greater than, less than, or equal to. Those are sort of three cases that we can go in. And because when we start splitting into cases, we want to be exhaustive and make sure we cover every case. In general, we're going to cover those three cases. Now, if you could cover all three all at once, then you don't need cases at all. But sometimes we'll lump the equals case in with one or the other two cases, and that's what I'm going to do here. So when I say, we're considering two cases, I'm going to have one case. This is going to be my first case where OI starts later than PI. So in this case, we know that OI starts later is a greater than relationship in terms of the starting time. So our other case, case 2, will be the less than equal to case. It's OI starts earlier or at the same time as PI. So, but we're going to start with case 1, OI starts later than PI. Now in this case, let's be careful here, because remember that our algorithm says we're always going to select the non-overlapping class with the latest start time. So if O selects a class that starts later than us, we select the one that is non-overlapping with the latest start time. So if you pick one that starts later than us, you must violate this part. You must pick an overlapping class. So that's the argument that we're going to make here. We always select the class with the latest start time that does not overlap with the previously selected classes. If OI starts later than PI, then it must overlap with the previously selected classes. So what does that contradict? Non-overlappingness was assumed right here is a condition of validity. So this means that our O is not valid. Well, that's a contradiction. We assumed it was optimal. We assumed it was valid. So this first case leads to a contradiction because it's impossible. We always select the latest start time with the non-overlapping classes, but O could not select one with a later start time without violating the non-overlapping class criteria. Okay, so we know that it can't select a later one than us. Well, what if O selects a class that starts at the same time as P or earlier? So here I've stated that as starts no later than PI. It might start at the same time as PI, or it might start earlier than PI, but it starts no later than PI. So if this is the case, now I want to remind ourselves that we might be in a tie situation. There might be more than one class we can pick to achieve our maximal sized set, and we're in a case where we just happen to have a tie. We broke the tie in different ways. So remember, in this type of argument, in this case, we want to do what I've been calling a swap argument, or a surgery argument, where what we're going to do is we're going to take O and we're going to do some surgery on it. We say O is optimal, that's what we assumed, but it's the wrong optimal one. There's more than one optimal solution for this problem, and we accidentally picked the wrong one. We want to pick the one that agrees with us. So we're going to do surgery on O, making sure that it remains valid and remains optimal in doing the surgery, but after we're done the surgery, it will come out O prime, and O prime hopefully will still be optimal and valid, but now will agree with us. It will now select PI instead of OI. So let's see how we're going to do that. So we're going to do our surgery, and we're going to create O prime. And the way we're going to do it, fairly straightforward, is we're just going to take OI out, and we're going to add PI in. Okay, we're going to take OI out, and we're going to add PI in. So very straightforward surgery. Pluck out the one that we don't like, put in the one that we do like. Okay, now, the first thing I want to mention, well, let's remind ourselves, what do we need to prove here? We need to show that that O prime is still valid and it is still optimal. To show that it is still valid, what do we have to do? We have to show that there are no overlaps. So we have to show that pi does not overlap with any of the other elements of O. Okay. In particular, the ones that came before, and the ones that we added before rather, and the ones that we would add later on. Okay. Second, we need to argue that it is still optimal. To be optimal, we need to know how many classes fit here. Well, we've removed one and we've added one. So actually the optimality case becomes free. The size of O prime is the same as the size of O. So we just need to make sure that it's still valid. So let's continue here. Okay. So remember, for validity, we want to make sure that pi does not overlap with any of the other elements of O. So I'm going to start with all the elements we added beforehand. So these are the elements O1 up to OI minus 1. Now remember, when we start out our proof, and it's important, this part we sometimes skip, but it's an important subtlety. This idea that we're saying let I be the first class in what order? In descending order of start time, such that they disagree. That means up until this point, they have agreed. So O1 up till OI minus 1 is the same as P1 up to PI minus 1. And since PI doesn't overlap with any of them, we know it doesn't because our algorithm never puts in overlapping classes, it must not overlap with these ones as well. They're the same classes. So all the ones that were in there before don't overlap with the ones we have now, so we're good. What about the ones that were in later? Now, here's what's going to come into this one is that OI starts no later than PI. All the ones that we would add after this point are actually ones that come earlier in the day, because our algorithm backtracks, remember. So all those ones actually finish before OI starts. And we're going to take out OI and put in PI, right? Because those ones all finish, so OI plus 1 up to OM, all finish before OI starts. We're going to take that out, we're going to put in PI. Well, OI starts no later than PI. So that means, another way of saying that is PI starts after OI, or maybe at the same time. So that means if all those classes were already compatible with OI, and PI starts later, then, well, of course, they will be compatible with PI as well. So we've now argued that the ones that came before were compatible, the ones that came after were compatible. So PI must be compatible. So in this case, we are valid. Okay. If we're valid, because no sets overlap with one another, then on to the next one. I already argued optimality is just about the size. We've added one and we've removed one, so the size has not changed. So after our surgery, we have a valid and optimal solution, O prime, and O prime does agree with P in that it selects PI instead of some other class. Okay, so after the replacement, it now agrees with P at point I. Now we're done now, but really I usually like to finish by saying we're done. So we're going to say, okay, case 1 was a contradiction, so that'll never happen. Case 2, we said, well, even if the optimal one didn't agree with us, there was an optimal one that did agree with us. So if we repeat that argument enough times, we'll eventually find the optimal solution that agrees with us on all of the choices we've made. Therefore, our solution is one of the optimal solutions. And we're done. Okay, so let's bring in a little bit of context here. So what have we done? We've proven that this little subroutine that we have here for finding the maximum non-overlapping set works. It will always find the maximum non-overlapping set. So we had that built inside of Bob's algorithm. So let's see if we can apply Bob's algorithm right now. Now the way I'm going to do this, we've already run the algorithm, and the first time we ran it, we got this set. So we would take those and sign them all in to one classroom. So I've colored them all the same. So we could do that again. And it looks like if we do it again, we'll get this set. And I've just, looks like that's not a tie here, or at least that's a permissible solution there. So let's say we had that set. Let's see how many classes we've got. Again, I'm just running that algorithm again. The next algorithm, latest start time starts with this one here. We get the green ones here. Continuing again, the purple, Again, with this set here, the blue, looks like my orange class, and then the black class as our last one. We can count 1, 2, 3, 4, 5, 6, and actually this other color blue, 7. So we actually have 7 classes, which we did calculate last time was the minimum number of classes that we would need. So Bob's algorithm actually did work for us here. However, we haven't proved that Bob's algorithm is correct. And that's really the next thing that we would want to do. So as it turns out, Bob's algorithm actually is not optimal. And we can actually find a counterexample for it. I found one using 6 classes. I don't know if we can find one that's smaller. But the idea here is we want the proper assignment of classes to not assign the maximal number of classes into one classroom. That should not be optimal. And so to do that, we have to kind of set up a strange situation. I did with 6 classes. Let's take a look here. You can notice here that the maximal set of classes that we can assign to one classroom is of size 4. But if we use that classroom, the other 2 remaining classes that we have left over are incompatible with each other, so we end up using 3 classrooms. However, the optimal solution is, as I've got depicted here, using 2 classrooms instead. So actually Bob's algorithm is incorrect. So why focus in on Bob's algorithm? We have a correct algorithm for the subroutine, the maximal non-overlapping set, and we might need to solve that for other purposes. But what about Bob's algorithm for scheduling classes? Well, actually, his algorithm is not optimal, but it's not that bad. In fact, we can show, and we'll show here to finish this video, that it's never going to use more than k log n classrooms, where k is the optimal number of classrooms. So it's never going to use more than log n times more classrooms than we would have used in the optimal case, which maybe would be something you're okay with if you didn't know how to get the optimal solution. Alice's algorithm is technically better, but let's see if we can prove here that Bob's algorithm is at least not that bad. It can get close. Now, for our example here, let's just maybe do a quick piece of math here. We can see here that there's a couple pieces here. We have n equals 6. We have 6 classes here. And we've got how many classrooms what's our optimal case? Our optimal case is 2. So we've got 2 classrooms. So what is k log n? Well, we need k log 6. So k is 2, so 2 log 6. Log 6, we're actually doing base 2 log here. So in our base 2 log of 6, I'm gonna wave my hand at it, say it's about a 2.5. But that's just because I don't want to go punch in my calculator. I know it's greater than 2 and less than 3, somewhere in the middle there. So what's in the middle? 2.5. Okay. And what is my k? We said our k was 2. So 2 times our 2.5 is about 5. So this is saying our algorithm will never return with more than 5. Well, that's true. Ours came back with 3. So that was within the range. Okay, so that's how we can apply this result. But let's see how we can prove this result. So again, I'm going to start here with my theorem. That's just the same theorem as we had on the previous case. Given some arbitrary set of classes, if the optimal solution is k, then Bob's algorithm will return no more than k log n classrooms. Okay. Starting off the same way as before, we're going to assume we have our arbitrary set, but we're also going to assume this part, the antecedent of our conditional, right? At the beginning of our if statement, right? So we'll assume that's also true. So assume our optimal solution requires k classrooms. What are we doing here? We're really just naming what the optimal number is. We're going to call it k, so we can use it in our math. Okay. So the idea behind this proof is we're going to argue how much we're shrinking the set by each time. Remember, the idea behind Bob's algorithm was take a big enough byte out, and that should minimize the number of bytes that we take every time. Okay, so let's, again, this next bit here is just setting up some notation. So let's say we do t iterations, okay, and then we want to say nt is how many classes we have left after t iterations. Okay, so n0, after 0 iterations, we have n, all of the classes. Okay, so we're going to use this to figure out what t is, how many times we have to do this before we get down to 0, basically. Okay, now, one thing we'll know is, by assumption, we know that all n of these classes can be covered by k sets. Okay, so that means that at any one time, that if there happens to be n sub t classes we need to cover, there has to be at least one maximum. There must be at least one classroom or one set of classes that will fit into one classroom of size at least n over t by k. If we couldn't do that, if we couldn't fit at least this many classes in, then we wouldn't be able to fit them in k classrooms. We'd need at least k plus 1 classroom. So because we know we can fit them in k classrooms, there must be at least this many that are going into at least one classroom. Okay, so this means we can use this. We can say that we're using Bob's algorithm after one step. So that's my next step. After one step, if we used to have n over t, now we're going to minus over this much, at least this much we're going to take away. So at the next time point, we're going to have less than or equal to, because we might be taking away more than this, but we're going to have less than or equal to what we had in the last time step minus how much we take out by that group. Okay. Now, just factoring out the n over t here, we get this equation here, 1 minus 1 over k. Now, this is an interesting equation. It has lots of interesting patterns. As we'll see in a second, we're going to use it in a formula. But we use this in a number of cases. It's going to be helpful for us in our approximation right now. Okay. Now, we're just going to generalize this one step further. If this is one step from t, this is what t plus 1 is out of t, well, then if we wanted to go 2 steps, we're just going to multiply by this factor again, 1 minus 1 over k again. So if we want to do it t steps, we multiply it by this factor t times. So we can now express what n of t is. N of t must be less than or equal to the original n of 0 multiplied by this t times. And the original, of course, was just n. So now we have what n of t is in terms of n, t, the number of ticks, and k, our optimal solution. Okay, the next step here is to use a fun sort of cool approximation. Now, rather than try and algebraically or mathematically prove it to you, I've just got a depiction of this right here. In fact, I've got e to the minus x instead of 2 to the minus x, but 2 to the minus x is just a little bit deeper here. You can see 2 to the minus x still passes over this line, and we can verify this. We're actually only interested in this range here. When this value here, 1 minus x, where this 1 over k, so here I'm talking about 1 minus x, so x in this case is 1 over k. Since we've got this expressed as 1 over k, right, where our k we assume is positive, then that means we're going to be in this range here, okay, between 0 and 1. So since we're selecting that off, we're going to approximate that by saying this value, 1 minus x, which is this straight line, we're going to say it's less than or equal to this curvy line here, which is 2 to the minus x. All right. Now, in that formula, our x, remember, was this 1 over k. So I'm going to swap that out here. We're going to say here this 1 minus x is less than or equal to 2 to the minus x. Where 2 to the minus x here is now 2 to the minus 1 over k. A little more simplification, bring that t in. We get this formula here, n times 2 to the minus t over k. Okay, now our goal here, our n over t here is less than or equal to n times something. Well, what we want to get here is we want this to cancel out with our n to be about 1 over n. So we're going to go and we'll notice that if we go and plug in a particular value for t here, if we plug in k log n, so think about plugging in k log n for our t, we see the k's will cancel out, leaving us with 2 to the minus log n. Okay. Well, 2 to the log n is n, so 2 to the minus log n is 1 over n. So we get n over n, or 1. So after t steps, where t is equal to k log n steps, we'll have less than one class needing to be covered, meaning we're done. Okay, we've covered all our classes. So how many steps do we need to do that? In the worst case, k log n steps. Okay, so we're done. So after k log n steps, we'll have less than one class needing to be covered. Okay, the purpose of this last proof, just to recap, was to argue that Bob's algorithm, despite not being correct, giving us the optimal solution every time, would give us within a bound of the optimal solution. And again, it's sort of up to you to decide if that bound is an acceptable bound or not. And of course, if you already know that Alice's algorithm works perfectly fine for this problem, then I'd say this is not an acceptable bound for me. I would prefer to use Alice's algorithm. However, there are a number of other problems out there where we might have no known solution to the optimization problem that is not really inefficient, where we might have a fairly efficient approximation algorithm. So a lot of problems that are what we call NP-complete problems, and we'll be looking at these in more detail in a future video. These problems, the best known solutions are exponential, but we might have nice, good, efficient approximation algorithms. Okay. So I leave you with this just as a taste of what an approximation algorithm is, and our first proof of what a bound on our approximation algorithm. But in our next collection of videos, we're going to go back to just standard algorithms where we'll prove correctness of the algorithm, achieving the optimal solution every time. All right, thanks a lot for watching this video, and we'll see you in the next video.